Okay, so you can see this graph. If you make this picture looks very good actually when you display on your presentation. Okay, so you can take any view like this. Okay, so y plus is maximum y plus is 10, and please note that the file I'm going to provide you, that file will contain the data which is shown here. Okay, so that file also has the y plus, maximum y plus is 6, and y plus is making the lot of difference in the data like a drag coefficient, other things. So definitely I would suggest that you should run the cases with the 2 or 3 meshes, and then you have to find out that the which one is going to give you the results which are mesh independent. Okay, this is very important step, and that we will cover also. So anyhow, right now for demonstration purpose, for the teaching purpose, this is okay, and definitely we will go through the mesh independence steps as well. So this is the wall y plus on the in the like in terms of the contour plots. And now if I go for the xy plot, then definitely I will go for the turbulence, and from here I will go with the y plus, wall y plus, and the z coordinate 5, and click on the save plot. So you can see the maximum value is on the leading edge, and average value might be around like a 3 or 3.5 or 2.5 in between those values. Okay. So okay, now the next thing is that I want to post process these results in the CFD post as well. So that you can do like many things we can do here, that I will go step by step. One of them is that you have to find out the drag and lift coefficients in the CFD post, and we will compare that what is the like a similarity in the fluent and the CFD post. They are giving same or not. Okay, so results should be similar or same, exactly same. So now in order to open the file, what I'm going to do is that this is true for the both cases. Okay, so I will double click on the results, and this will open the CFD post. Okay, so here what I did is that for example, if I like tell you that how to do this thing, so let's do it on the fresh copy. Okay, so here I didn't do it, so for zero angle of attack, so I will tell you that how this can be done on this case here. Okay, this was already done, that's why you can see this graph here. Okay, now I'm going for the few expressions here, and our final goal is actually is to create the expression for the drag coefficient and the lift coefficient. But for to define this lift and drag coefficient, what we need is that we need the new coordinate frame. For zero angle of attack, new coordinate frame is not required. Okay, because it's already on the zero angle of attack. But for other angle of attack, there are two ways to be doing that thing. One is giving the angle of attack, but that's like that is done in the CFS, like in the CFS pre, and then we can get the results directly there. But if you are doing it in the fluent and then getting results to the CFD post, then the only way is that to get the data for the some angle of attack, you have to define the new coordinate frame. So I will define it for zero angle of attack, and same is done. Only difference would be the their angles, angle of attack, that will vary in the both coordinate frame. Okay, so here I will go to the like these are expressions for the lift coefficient, and the formula is that the lift coefficient is a lift force and divided by the 1/2 density at the infinite, means at the inlet, velocity square at the inlet, and the area of the your 3D wing. 3D wing is like I told you, this is having the this like span wise is a 0.3, and its chord length is 1. So overall area that is facing the wind is going to be equal to the 1 into 0.3, so it's going to be the 0.3 meters square. So why we are doing this thing? Because when we divide by the area, this will be non-dimensional quantity, and it's irrespective of the both dimensions, length and like a chord length and the span-wise direction. So it is independent of these values. This is now, once we divide by the 0.3, now they are like a per unit area. Okay, they are now going to be per unit area. So this is valid for the any case. And if you have the sum, like you want to make the calculation for like a forces dimensionally, then you have to multiply with that area. For example, my wing, new wing is 1.3 meters. Then I will multiply with the 1.3. I will multiply with the 0.5. I will multiply with like a same thing here. So if I want to get the drag force for some other like aerofoil length and the area, so I will multiply simply the CL and CD by the 1/2 density, velocity square and the area, and I will get the force for that particular dimension or the particular material properties and the flow properties. Okay. So now what we want that these are should be defined like area, density and the velocity with the proper units. This is very important. If you define the some quantities directly, like I am defining area directly here, so it's a 1 meter by 0.3 meter. So either you put the directly 0.3 and then you have to put in the brackets meter square, or I'm putting the 1 meter into 0.3 meter, then it will directly calculate the units and they are going to be meter square. Units should be like they should mesh very well, otherwise we will get the values, they are okay, but the units will be wrong. And when I define the mass flow average of the velocity at inlet, because it already is containing the very like units, that's why we don't need to put the units in the expression here, because they are taking units from the CFD post itself, and the CFD post is taking data from the fluent. And same is the case with the density. Okay. And then after that we define this function and these values here, and that's all. Okay. So now go to CFD post and go to expressions. So first thing is that I will define the density. So density, it should be a variable like a expression name that does not contradict with any other defined inbuilt name in the CFD post. Okay. So right click here and I'm going to use a CFD post, and mass flow average is very good for these definitions. Okay. And what we are doing with the density here. So find the variable that is the density, and where it's going to be on the inlet. Okay, location is the inlet, and if you apply you will get the units and the value as well, and it should be 1.225. Okay, so density is defined. Next is the like area aerofil. So I will put the name in this way, so that the area might be a name of the some inbuilt functions expressions in the CFD post. That's why I define the name. So that should be unique to like our own area, our own variables. Okay, so it's 1. So put the square bracket, and once you have the correct units, they will be converted. The units will be converted into the italic fonts. Okay, you can see it. Multiply with the asterisk symbol, then the 0.3, and then again put the units of the meter and click and apply. So this should give you the 0.3 and correct units, which is the meter square. Then I would get the velocity at the infinite. Okay, infinite means that the far away from our main geometry that is on the inlet. So velocity infinite, and this is going to be the mass flow average. This is the velocity magnitude, so velocity only, and at the inlet. Okay, and it should be giving you 43.8. that is that we defined the value at the inlet. Okay, now I'm going to define the, before that I will go to outline, and I will make the new coordinate system here. Okay, and that you can directly put from like here. Okay, this one. You can also do it from the insert, and from here you can also put the coordinate frame. Same icon, same thing. So one is from directly from the screen, one is from the menu. So you can put the name also, like you can say coordinate frame 0 angle. Okay, 10 degrees, whatever you want to put. So let's say I'm saying it's for angle of attack. Okay, so now First thing is that simply click on the apply. Okay. Reduce the symbol size to the 0.3 so that it should be like it's okay for if you take a look from the outside from here, this is now properly visible. But if you zoom to the Airofil, this is slightly bigger, okay, or too bigger. So symbol size, if you make it 0.3, this will be over here, okay. Now see, there are the three axes. One is the z axis that is normal to the xy plane where the our angle of attack will be there, okay, and two of them are the x and y axis. So first thing is that we have to fix our z axis and our origin. So origin, if I going for the moment coefficient, then I will be putting the my reference frame at the 0.3 or 30% of the chord length, okay. In that case, my origin will be at the x is equal to, now this is x is along the flow direction, so definitely that will be along the chord length. So I will put the origin at the 0.3 on the x direction, but this will make the my z axis inclined. So this the z axis point should also move in the x axis, and then it will make it a straight line. Okay, this is how the origin z point works. Okay, so they should be in the same line. Okay, the xz plane point is the first point is and second point, they are defining the maybe that the in some cases our aerofoil is along the z and y axis, okay, zy plane. So yz plane, in that case we have to play around with the z axis point. That axis point in that case would be the next direction, maybe the x axis is going to be our z axis. Okay, so then you have to put the particular point of z axis at that location. Okay, right now z axis point is on the 1, that means that the x, y and z coordinate 1. So this is in the z axis, but z axis may be like a third axis may be in the along the x axis, then you have to put the 1 here. Okay, now here you have to put the only coordinates of the our angle of attack. So it's only x and y. Right now this is on the xy plane, so x and y. So for example, I'm just giving example. If my angle was 45 degrees, then I will put the cos of 45, and this is sine and cos 45 will be exactly same. So I will put them, both of them here. Okay, so they are at the 45. So x-axis is important here actually. This is under 45 degrees, and the y-axis will be at 90 degrees. So now this will be at the 135 degrees. Now take example of for maybe for the, although it's not necessary because we have the y forces already in the CFD post. But if the y forces was not there, then to get the y lift force, we have to make the a coordinate frame that will be where the x-axis will be along the y-axis. In that case, I will put the 1 and 0 for the x-axis. So this will rotate completely by 90 degrees. Okay. And for 10 degrees, definitely you have to put the value of 10 degrees. That is like a second case. And copy. And paste in the x-axis. This is we define the angle of attack for the x is the cos component and y is the z component. So this is a sine 10 degrees, and you have to put over here and apply. So now this is a 10 degrees angle of attack. Okay, if we increase the size of the our symbol, so this is now 10 degrees angle of attack. Okay, and this is the procedure that to get the drag and lift coefficient in the CFD post. Secondly, the benefit is that once you have the you are done with the hard work, then the whatever values you put in the table and you run the new case with the new angle of attack, just change the coordinates here, and the data will be directly given to you from in the table. So unlike the fluent that you have to calculate data every time, once you calculate the drag and then you have to calculate the lift coefficient every time, put the angles and reverse and their sign, and there's a lot of hassle there. But in the CFD post, this is much easier. Once you do the hard work, then everything is very smooth and streamlined. So let's say definitely now for this case the angle of attack is 0, so we have to put the 1 and 0 here. And for 10 angle of attack, we have to put the proper x and y components. Okay. Okay, now go back to expressions. Now I will define the new expression. This is for the lift coefficient. Okay, so I will put the value that is just from CFD post, and this is a force X here, okay, and where this is going to be on the Airofil, and divided by what? Divided by the zero point 0.5 multiply with 1 upon 2 density velocity square into the area. So expression of the density, then the area square. So area square will be there, that is again like expression. So this is the area aerofoil, not area, but the first we will go with the formula that is the 1 upon 2 1 upon 2 density into velocity square. So velocity infinite velocity, so velocity at the infinite, that is the here, and to put the square we have to put the this cap symbol and then 2 and multiply with the area. Okay, area of aerofoil, and then close the bracket. But this is going to be now, see, the value of the lift coefficient with the just force x will give you the force along the default coordinate system, which is that x is along the x-axis and y is along the y-axis, no angle of attack. So now you may ask the question where the coordinate frame will be put. So this will be put over here. So you have to on the x you have to put the 1 hyphen symbol. Okay, then go to the outline, and then you have to right click here and click on edit in like command editor. Why I'm doing this thing? Because I want to exactly copy the that spelling. Okay, sometimes you type the same thing, but because of the capital letters or small letters, this will make the problem. Okay, so that's why I'm doing it. I'm directly copying from, because this is already from the from the CFD post. Okay, so here you have to paste, okay, and apply. So the value will be same definitely, because this is already defining the zero angle of attack. But with a 10 degrees angle of attack, you have to put the, simply you have to go back, and you have to simply change the coordinate frame values here. Okay, now I was telling you that the benefit is that if you make a table here and simply go to expression and put the lift coefficient, you get the lift coefficient here. Okay, so it's you can write it down, it's a lift coefficient. Okay, okay, now the second expression is for drag coefficient. So new, and this is the drag coefficient. Okay, sorry, this is the first one is actually this is the drag coefficient actually. Okay, so duplicate, this is the drag coefficient. Okay, this is a drag coefficient, and lift coefficient will contain the force in the y direction. So make it y, and click on apply. Okay, and here you can change the units and make the units as the simple fixed one, and maybe you can make the digits, number of digits to the 4. Okay, okay, this is the lift coefficient, and the drag coefficient is going to be the drag coefficient. So expression and the drag coefficient. Okay, so this is the lift coefficient, and this is a drag coefficient, and you have to put the scientific to the fixed one, and number of digits are equal to 4. This is the drag coefficient. Okay, I told you values are slightly varying than the values I have in the slide, which is like on the main slide, which was most important slide in the this workshop. So that contains a slightly variation there. Okay, in the drag maybe it's maybe lot of differences there. Like it's a 0.225, and here is a 0.0173. Lift coefficient is 0.0123, and it's a 0.0125. So it's like lot of small difference here. It's a okay, lift coefficient. Okay, so the lift coefficient let's make the again the function here. Okay, so the force y. Okay, now this is corrected. Okay, so sometimes you have to take the directly the spelling and everything directly from CFD post. So now you can see that our values of the drag coefficient is 0.0123. Here is a 0.0173, and so this will like this is more accurate here. This is more accurate here. Okay. But the lift coefficient is coming out to be the 0.2225. That's the problem actually. So let's work on that thing. Okay. Okay. So I verified the results, and it turns out that we were comparing the 10 degrees angle of attack case, and our case was the 0 degree. Right now I was explaining. So here. Okay. So I ran the case actually for the some iterations also, that so that I can confirm that it is not because of the solution, but it is actually a case of the 0 degrees angle of attack. Okay. So the lift coefficient is 0.2225, and this is the same, almost like a closed to this value. Okay. So point double two triple two five, and in the previous case was the point double two five, and the drag coefficient is 0.0123. This is like a higher on the higher side, and from SST it was 0.00942. Might be that the SST was predicting the like laminar turbulent transition slightly, but it was predicting, and that's why it was only a 17.75% error, and at higher angle of attack error is more. So now I think you get the idea that how to get the values of the lift and drag coefficient in the CFD post through the expressions. Okay. Okay, now you can display the vector plots as well. So that we display on symmetry 1 and apply. Okay, here you can like go to symbol and make the symbol size initially that 0.1 or maybe less values. Okay. Okay, let's make it 0.04. Okay, let's make it 0.01. Even less value. Okay. Okay, here let's make it the 3D arrow like this one. Okay, here you can clearly see that the development of the boundary layer on the aerofoil upper surface. Okay, here I can change the aerofoil color as well. Let's make it gray and apply. Okay, so I think now we have completed the like a lot of things in this case, and you can also display the like path lines. You can display the contour plots, which we already did. So let's display on the aerofoil surface. Okay, here you can display the like mesh lines and make the color as the black. And don't display the any faces. Okay, click and apply. Okay, so this will be like a nice picture for your paper or for your PowerPoint presentation. Okay, and secondly, when you're displaying the contour plots, here you can like change the number of levels to the like 20 and apply. Labels, you can put the numbers also on these levels, and there are show color bands, okay, like this, and you can also turn off the color lines. And secondly, you can make the color lines color to be a single color, for example the black color, okay, like this. Okay, so I think now the workshop is complete, and let's uh, see the other things if required. So if you have any problem, please let me know. If you have any questions or queries, please let me know. Thank you.